Okay, let's get started. Okay. So this is lecture number 5, and this is right after assignment number 2. So I just want to briefly discuss assignment 2, and then we can resume where we left off. So um, so today's lecture is going to continue where we left off. Basically, last time I think towards the end we were talking about naive-based classifier. Today we'll talk about latent initial allocation and a few more things. But before that, I wanted to talk about two things. First is I hope assignment 2 was okay in terms of complexity, because it's not complex. It's just that if you're going to do CIFAR 10 on a non-GPU machine, it's going to take a long time. Okay, and obviously I've been repeating this about a couple of times now. There's this notion of data sets, data loaders, transforms. Those things we saw, for example, in the LoRa example, but you would see the same pattern actually in the fine tuning and peak switcher extraction script. And the easiest way to do the assignment 2's question 1 is actually to just clone the we have an ants versus bees example in our repository as well as on PyTorch's tutorial, whatever subdomain. And you can start with that because essentially you're changing the number of classes from 2 to 10. And I think that's about it. And there's something to surface like what's the most correct and what's the incorrect examples, but that's more just Python coding, not really more than that. Let me just show this first. And yeah, and then you would have seen how would you extend like the definition. I don't know if you got to see the definition. Like if you could print, once you load an existing model, you can always print its summary to get a sense of what are the layers involved. But otherwise, it's pretty straightforward, except, model.parameters, you can freeze those parameters. So required grad is equal to false, basically. So any challenges with question 1, other than actually going through and understanding the code? That's the challenge with question 1 is not really executing it. If you understand the code, that's actually going to be helpful for a long time, because that's actually the big delta. So far you've been looking at smaller models mostly. In assignment 1, we did not. We looked at one, Keras type of a model for MS. But really, this is the delta where you kind of really work with and something which is not tabular data. Because even MNIST is not tabular, but then you just vectorize it, and so it's basically a long feature vector, right? Yeah, so no issues with question 1 then, I assume, or do you guys have any questions or comments about this? Do you guys remember solving this? Because yesterday was the deadline, right?
Me and my remember setting GPU issues with just has computation models, but that's about it.
Yeah, there's it's not too high. I mean, this is a really small data set. But yeah, it's a good data set. This is one of the smallest data sets to get a feel for why a GPU is necessary compared to just working with a CPU. Necessary in the sense that it's a nuisance. If you can obviously use a CPU, it's just going to take a long time, and you'll kind of lose patience. Okay, yeah.
So I had one question to fine tune it. So like one of the things that I was trying to do was I was like increasing the number of epochs, and I was like also like so I increased the epochs from 5 to like 11, 12, and then I got the learning rate down from 0.01 to 0.001.
Sure.
But still my accuracy wasn't improving, it actually went down. So
accuracy going down. Accuracy. Oh, but how are you tracking? Oh, you're able to. Okay, you're tracking accuracy as well as an additional measure, not just a loss curve.
no.
But what about the loss curve? Is it also going up? It should probably not.
I didn't check the loss curve, but
Okay.
like originally it was at 80%, which I thought
No, accuracy on what? Like train data or like validation data?
on the validation.
That can, right? I mean, we just saw overfitting example last time where you saw the hockey stick curve, right?
But like just increasing like from 5 to let's say 11 to
Yeah.
that, like would that have such a big impact on?
Yeah, that's what we saw, right? I mean, the number of epochs might not be 5 to 12 versus 20 to 40. But last time, I mean, although last time the curves that we saw were actually loss curves, but you saw that the validation loss was actually blowing up. So validation loss blowing up is equivalent to saying, or has some good correlation with validation accuracy going down. So it can happen.
And also, is there like any good way to like do this iteratively without me manually doing it and like finding the best balance between accuracy, the best balance between the epochs and the learning rate?
Balance with epochs versus learning rate. So generally, epochs you can continue to train over, for a long number of epochs, except that you could checkpoint and remember what the model was at every epoch, right? You can always remember what the model is. Doesn't like download the model wait start save, for example, so that you don't have to rerun epochs. But yeah, the choice of learning rate decay as a function of epoch, that is not. I mean, it's a search space of how the decay should happen. So that's a hyperparameter search process. So there are tools. I don't think in that script we are not using any other tool other than PyTorch and Torch Vision. But there are tools which help you search over the space, whether it's random search or some sort of directed search, or just gridding and like trying every decay rule or something. So there are multiple paths there. It's just that I don't want to name any tool, but there are actually popular tools there. Yeah. Optina, for example, is one tool. I don't know if you guys have used. Optina is also useful for scikit-learn and other modeling packages. Yeah. Okay. Thanks for the comments about that. The second question is, again, I did discuss it before, last week, but anybody had any challenges with this? Again, if you do it naively, like even just forget about the modeling part, even if you want to compute Xij, if you don't know how to like set up the for loops, perhaps it might take a long time, but you will be able to at least save the results. And yeah, so this could, just generating Xij could take some time, and it requires a little bit of your decision making, because the statement says users that liked both movies INJ, not just watched movies INJ. So you could look at how many user IDs match for a given movie, 2 movie IDs, how many user IDs are common to them, but not just common, but also might be greater than 3 rating or something. Could be your decision to make of what is meant by liking the movies.
So rating is equivalent to liking.
No, but the rating of 1, for example, is not really liking, right? Yeah. It's up to you. This is just, I'm just trying to show that even questions like there are textbook questions which will also have gaps. This question has an obvious gap. And there are some situations where there's complete gap in the sense that you just have to come up with whatever design for how you can construct your solution, right? By gaps, I mean gaps that you need to fill, like assume things. Okay, let's say Xij you somehow computed. The problem is there will be some pairs of movies for which there is no common users. Okay. So what do you do with those situations? And there will be actually a lot of movies where there's no common users, at least. So the question is that then supposed to be 0 users, or you don't care about that movie pair? Okay. It could be, it's not that, like for 2 pairs of movies, if somebody had watched it, maybe they would like both of them, but there's no common person who watched both of them. Does it mean that it should be 0, or it should be left empty, as in like that IJ pair you don't consider in your loss function at all? Like, for example, because in the loss function there is a double summation going on over all movies, so there could be pairs of movies for which Xij is basically 0 because there's no common users at all. Then the question is that term even appropriate? Because you could think of a situation where only for those movies where there were common users, how many like them would be a useful, could be those terms that appear here. And for movies that there were no common users, you don't even know who the common users are. So, at least the dataset doesn't support any common users. So you can't even say who among the common users who liked it, how many numbers liked it. So there is some nuance here. So I'm not saying one is wrong and the other approach is correct. It's just that there's some assumption built in, okay, with both choices. Do you guys understand what I'm trying to say, or does it make sense? This side, yes. This side, no. Yeah. Okay. Okay. So that once you understand these assumptions, in whichever pathway, the question is, how do you set up this problem, right? So, how many of you had some challenges with setting up this loss function and actually training the VI and VJ parameters? There's another thing that you need to choose, which is the dimensionality of VI and VJ, right? So as in, like, what is the dimensionality of these vectors? Like, are they 5 dimensions, 50 dimensions, or is the number of dimensions equal to the number of movies, right? So there's some choices. One choice you should not be doing is the number of movies, because that doesn't make any sense at all. Okay. Any comments there? No. Why doesn't the number of why doesn't the dimension being equal to the number of movies make sense? Any intuition?
We're looking at combination.
So it should be more than that. Like, I'm asking about the dimensionality of the vectors v1 to vm. There are m of them, but what should their dimension be?
Should be less than the number of movies.
Yeah, why? That's why I was asking.
So it's
Depends.
Yeah.
Depend on the users, how many users are there, unique users. Dimensionality will be.
Oh, you're saying this dimension should depend on the number of unique users? What is the number of unique users in the data?
It's approximately 7,000.
And how many movies are there?
9,000.
It's 9,000.
So you're saying the dimensionality of V should be 7,000? Why? I mean, you get to choose, right? I mean, it's not specified what the dimension is, so you get to choose some number. Why not 5 or 10? Why can't dimension, right? So each V should be a 10-dimensional vector, is what I'm suggesting as a potential candidate choice.
Then how can we make a matrix out of 10 dimensions?
Why do you need to make a matrix out of these 10-dimensional vectors?
Particular occurrence vector of the.
No, VI times a 10-dimensional vector times a 10-dimensional vector will produce a number. We just want to see that that number is approximately close to this Xij that you computed beforehand, right? And you're going to adjust the coordinates of these vectors, which are basically the parameters of this model, to approximate this number, right? So the dimension of V is not, is something you got to choose, and that is not influencing anything here, right? So, I mean, obviously, the lower the dimension, you may not be able to fit all the numbers, but I don't see. So what are you thinking? Like, what is your hesitation for choosing, let's say, 5-dimensional vectors?
It might not be enough dimensions to capture the interactions.
Yeah.
It's just not enough. And then on the other side, I think you said earlier, you said it's the dimensions of the bottom of these. You would kind of think, just adding back, it's like, okay, we have that many columns.
Yes.
I guess not the right way to think about it, but then it would just be like a one-hot encoding for movies.
Yes. Yes. Yeah. So if your V's are the same dimension as the number of movies, then you're essentially, you can actually compute Vi transpose Vj to be equal to Xij. It's every time you can have a loss of 0. Why? Because you can just ensure that the entries in those locations, because Vi transpose Vj. Okay, let me trace back. That was not appropriate, but that was not correct. But basically, if you have m vectors and each vector is of length m, so you have like a m cross m dimensional matrix, right? And Xij or X, capital X, is also an m dimensional matrix, right? So the number of numbers here is kind of the same as number of numbers there, although there's an inner product going on, so I should not really comment, like that. So what I'm trying to say is this inner product here, if you think of a vectorized version of this, then you're basically multiplying two matrices, which is m cross m times m cross m. Outer product of them is equal to this one m-dimensional matrix. So you have too many numbers is what I'm trying to say. I don't want to, I'm not saying it properly because I'm not writing anything, but m would be too many. But anyway, so in general, I'm just saying that the dimension of V, you get to choose. That was the original point. Sorry, there was a lot of discussion here, but you get to choose whatever you want. So there is no a priori preference. Obviously, the lower the number of dimensions you pick, like 2 or 5 or 10, you may not be able to fit all these numbers, these Xij numbers. But if you pick the dimension of V large, then you will be able to fit these numbers. Okay, so it's some form of regulating the complexity of how expressive your vectors are to fit all these data points. Okay, so think of the other extreme, right? Instead of capital M as a dimension, we take 1 as a dimension, which means that these VIs are just scalars. Then you're just saying the number of, for every pair of movies, the number of users who like this is just every movie has just one parameter, and the parameter times parameter is going to be approximating the number of users who like this movie. So you can see, right? So that would be very limited because with single numbers, you may not be able to approximate like quadratic number of numbers, basically. Any comments here? So that was, anyway, that was the third design choice that you need to make once you're okay with the couple of previous assumptions that I mentioned, which is whether to substitute zeros, and then also what is meant by liking. Okay, other than that, there's technical details like how do you set up this problem using PyTorch? I mean, you don't have to use the nn.module type of flow. PyTorch, you can always instantiate these as torch, tensors, and by default, required grad is going to be true. And so you can write a for loop like for 100 iterations. For every pair of movies, I can just compute a final statistic, which is this overall loss, sum of the losses, and then you can just do loss.backward to compute the gradients, and then you can manually do the gradient update if you want. Okay, or with the optimizer.step if you instantiate an optimizer. So for this, what I'm trying to say is that there are a couple of ways to do it. One is using the nn.module way, where the inputs to the forward function can be the movie indices I, j, and then let's say batch size is 1. So you give an I, j pair, it produces a prediction which is bi transpose bj. That's its prediction in the model forward function. And then that prediction you just compare with xij and see you get a square loss. That's one way to do it. So that's using nn.module, where you have an init function and then forward function. Otherwise, you can kind of ignore all this torch vision and data set and data loader and all that. You can just write a for loop where all these tensors by definition, if they're in terms of computation graph, all these are used to compute a final loss statistic, then you can just do loss.backward and optimize as a step without using the nn.module architect pattern of doing it. Does it make sense what I said, or any questions here? How did you guys do this? I guess let me ask that.
Just in terms of like the optimization.
Yeah, how did you set up this problem? Yeah.
I used like the n.dot module, the forward and define the class.
Yeah. Yeah. Okay. Yeah, nn.module will be fine. But if you don't want to use that, that's also fine. You can just write a, you don't have to think in terms of nn.module structure and init and all that stuff. You can just say, okay, PyTorch, the nice thing about PyTorch is any tensor, any simple computation that you do, let's say instantiate a tensor and then square every element and then sum them up. If you want that you can think of loss, that thing as input, you can always do backward and compute the gradients of this computation that you did, squaring and summing as a function of the loss. Okay? So any function of tensors, you can actually compute the gradients. So you can explicitly do that without like a ML style writing of this code. Okay, I mean, I feel like some of these people on this side are silent, but you should check, there's some interesting exercises thinking that can go in here, just to appreciate more about how to set up PyTorch and how to set up some design choices, right? So far in the past 4 lectures, there's always in question of, how many hidden nodes, how many layers. Earlier there's a question about how to decay the learning rate if you at all want to decay it. So again, those are all choices, and there are more choices here that are surfacing up, right? Anything else about the assignment? Then I can switch to today's content. Okay. Before that, I just wanted to show another thing, which is this paper from August 2023. So it just says GPTs are GPTs, an early look at labor market impact potential of LLMs. Okay, and there may be newer papers now which have a much better analysis of this. But one of the interesting slides, or one of the interesting figures in this paper is they're just trying to understand like how much yeah. So this table 6 here, I've actually screenshotted it and I'm just zoomed in here. It's just showing mean exposure to GPTs by job zone. Just think of LLMs as GPTs are LLMs. In this case, this is by OpenAI folks, so that's why they're using GPTs. But any LLM, like any language support model, right? They represent the median annual income for each constituting occupation. And they have some numbers. So I think I've not explained what these. So these are supposed to be exposure numbers. HM. There's a definition there, but basically they have ordered it in terms of what is the preparation needed for different types of jobs, and what is the education needed, and these coefficients and some these. So up to this column, total number of employed is just data. Okay, it's just some slicing and dicing of the workforce. Okay, the columns here, HM, and the coefficients here, they are trying to kind of capture the exposure level to GPTs by GPTs. So higher the number means more exposure. Okay, so you can see that basically the numbers are increasing as a function of 1 to 5. Okay, so it's just trying to show that these highly trained, I guess, folks are the ones who gonna co-work. Basically, that's why co-pilots, I guess, co-work with GPTs are potentially, they have to evolve in their activities. Basically, in terms of their tasks, it's not going to be the same as 5 years ago. That's one of the takeaways. Obviously, you can say, oh, maybe they're going to reduce the number of workers needed and all that, but yeah, that could also be an impact. But in general, this is just hinting to that there has been adaptation in terms of how you work. One of them is obviously, I think today people use co-pilots for coding, right? So that's one example. But also people use it for drafting emails or marketing, whatnot. So there's actually the work has changed, and the nature of work has changed in some professions. Yeah, that's so. Actually, I probably didn't do a good job of like summarizing the table, but I did want to say that it's a good example to look at this working paper, which is, I guess, just to recap, this is table number 6 that we just discussed. Yeah, so basically that table and table 4 are basically saying the same thing. Occupations with highest exposure to GPTs. Yeah, so this is like, you can see that the exposure levels are pretty high. Exposure just means like where they might have to adapt their workflows, whatever they're doing. Okay, so this is just a tangent. I would encourage you to look at it. It's called GPTs are RGPTs, impact of LLMs on labor market. I mean, this is not the only paper. I'm sure there are other papers now, but worthwhile getting a sense of how the nature of work is changing. And you guys are in a very, interesting juncture where maybe before when you're doing an undergrad or something, it was not there, and now post if you once you get a degree, it's going to be there. So the nature of work is going to be different. So it's worth kind of getting a sense of the market and where you should skill and where you should train would be useful exercise. Okay. Let's actually go back to our lecture for today. Today we will continue. We are a little bit behind, so don't ignore the numbers L04 and all that. But that's okay. I think it's not really so much about speeding and covering material. So today we're going to continue where we stopped. So we kind of covered some natural language elements towards the end of last lecture, and then we also covered naive Bayes and shortcomings. Naive Bayes is exactly that, right? There's no word, there is no representation for a word. It's just an indicator of whether the word was present in the data or present in the feature, the input or not. Input as an indicator of the word being present in that email for which I need to classify as spam or not. And that's not really taking into account anything about language. It's just one-hot encoding, basically, right? Or equivalent of that. So we'll see today another model called latent digital allocation. It's a clustering idea, so an unsupervised learning problem. And it was invented about 22 years ago, so a long time. But it's good to kind of know that because it's a nice toolkit to add to your tools that you know. Then we'll also see, so I guess LDA is one of the goals to kind of get a sense of LDA. The second goal is to see that a CNN can also be used for a natural language processing task. And in particular, we'll look at just sentence classification or sentiment analysis. These are just input is a sentence, the output is a class, positive, negative, or one of these finite number of classes. And finally, we'll look at the notion of embeddings. Okay, that's actually the key idea. Although the type of embeddings that we'll see in today's lecture are going to be somewhat older generation embeddings, as in older generation representations of vector representations of words. It's not so much the way these embeddings were generated, because the techniques that we'll see today are a little bit old, but it's more about if you had embeddings, irrespective whether it's old method or new method, how do you slice and dice them? Just like we did that in the CNN situation, right? So in the CNNs, we said, okay, if we have embeddings, we can just project them into 2 dimensions and look at them. We kind of will do the same type of activity here. Okay, so it's really a kind of a slower introduction to NLP, just to kind of get a sense of embeddings and understanding their properties and so on. But at the same time, this is a nice case study of how to go from words which are inherently not numbers, and so they're not in vector space yet, to things which will be in a vector space. And so you could do similarity, clustering, and all sorts of activities in that vector space, where these will maintain some semantic information, which is not possible by, for example, naive Bayes or LDA or anything else. Okay, so that's the whole point. So to not do one-hot encoding, do something better than one-hot encoding. And what is that better thing? It's going to be to trying to capture semantically similar words to have similar vector representations. Okay, that's going to be the theme. So I'm going to keep repeating that sentence every few minutes, but that's the goal for today. Okay, and I will not comment on assignment 3 today. Maybe next time. But assignment 3 doesn't directly work with lecture 4. The content for today, but it does look at the content from next lecture. So okay, so you don't have 2 weeks of lead time from the material covered to the assignment. So what we'll cover next lecture would be part of assignment 3. So you'll have 1 week. If you kind of wait for the lecture and then start the assignment, you'll have about a week. But that's okay. I mean, I can focus on some hints for assignment 3 in the next lecture, so that you're a little bit more primed to do it. Okay. Okay. With that, let's actually jump into where we left off last time. Last time we discussed naive Bayes model. Okay, so just to recap, a naive Bayes model just assumes a joint distribution between labels and the features. Think of features as just an indicator indicators of whether the word is present or not in the input. Let's say email or whatever. If it's a sentence, it could be indicator of whether a word is present in a sentence or not. And then your target could be positive or negative, for example, if you're doing sentiment classification. And the assumption is that the joint distribution is such that the conditional probability of the features, this presence or absence of words, given the label, is just conditionally independent. Okay, so that leads to a simple estimation process and also a prediction process. The estimation process is going to be, okay, count the number of certain types of labels. Under those labels, count the number of times the word will occurring, and that's just the probability of that word occurring given the label. Okay, so that's just the estimate of that. And the number of times of a certain class is just going to be total data set in the denominator, and the number of times that class appeared in the data set. Okay, so these are just very simple counting and dividing type of statistics that you compute, which are the parameters of your naive-Bayes model. And once you have this, you can compute the probability of any label, which is the last equation here. Any label probability of y given an x would be proportional. So you can just compute this for, if you have two labels, then you compute this for both the labels, and then whichever number is higher is your prediction. Okay, whichever number is higher, that y is your prediction. Okay, and it's proportional to basically the counts. The marginal probability of this is essentially the marginal probability of y times whenever x is present, you just take that number that you estimated here, and whenever x is not present, you take the number which is 1 minus that over here. Okay, and you just multiply all those numbers. So very simple estimation process. Okay, so that's what we did last time as one of the models. And the second model that we looked at, just as these are warm-up models for just getting a feel for text processing. And just to, one last comment about naive-Bayes is that there is no capturing of any word information. Okay, there's no if there's a cat and a dog and a house, there is nothing that you're capturing when you're creating these estimates, and actually computing the probability of spam versus not spam, for example. There's nothing explicit, specific about a cat or a dog or a house or something else, airplane, that you're considering at all. Okay. Same thing with character level language model. Character level language model is just an illustration. You don't have to do character level. You can do word level language models as well. You can do more. You can do it at the level of 2 words. You can do it at the level of a sentence. Okay, so this is not specific to character level is what I want to say. And it's basically a very simple idea, counting and normalizing, that we saw in the previous slide. It's just the model is just saying, okay, given a corpus of text, which is just a collection of sentences, I'm just going to look at what's the probability of under the probability, for every context, for every situation, which is for every 2 characters that appear in my corpus, what's the probability of any other character succeeding these 2? Okay, so you basically look at, if I want to look at HE as my target, my current focus, then you look at wherever, where in your corpus HE occurs, H and E occur, basically one after the other. Okay, and once you isolate whatever the instances there are, you count them, and then you see in each occurrence, what's the next character succeeding them. Okay, so let's say they occurred 100 times, and then among the 100 times, the next occurrence of these 26 alphabets is some proportion, then that's essentially gives you the conditional probability of the next alphabet being something given HE. Okay, so out of the 100 times, maybe A appeared 10 times, then it's 10 divided by 100 is the probability of A coming if there was a previous 2 characters were HE. Okay, now why do you compute these types of conditional probabilities? Is because once you have a so once you have at least 2 characters that you choose, I think somebody was mentioning autocomplete last time. So let's say you choose 2 characters. Let's say it is HE. Then all you're doing is going back to these estimates that you computed from before and just flipping a coin. Okay, flipping a coin with that probability mass function, and then you get the next character. And then you add it to HE, let's say HEA. And then you again look at now E and A as the reference, as the context, as in E and A as your focus. And then given E and A, what was the probability that you computed for all the remaining alphabets? Maybe it's L, then HEAL would be your completion, and then A and L would be your reference. Given that, what's the probability of the remaining 26 characters? It will be some character, maybe T, right? Health or something. So T, then T would be the character that you pick. So it's just a sampling from the conditional properties again, over and over and over again. That way you can actually generate a sentence. It may not be coherent. You may generate something. And that's what a language model is. Its language model is actually capturing just the probability of next occurrences, like words or characters, given the context, which would be current occurrences and current words. That's all. So this conditional property is what a language model captures. And large language models are exactly the same thing. They also capture the same thing. Given the prompt, what should be the response? What's the probability of a response given the prompt? Essentially what they're capturing. Okay. So we saw this last time as well. So now let's look at something which steps up from there. And this model is going to be for the unsupervised learning setting. Even the previous language model is also essentially an unsupervised learning setting, although you can use it for other purposes. So for this next model, which is called the latent digital allocation model, we need to know what Dirichlet allocation means. We need to know what latent Dirichlet and allocation mean. Anyway, the whatever the names are in that model's name. But before that, we want to understand what is a distribution, a named distribution, just like a Gaussian distribution. Okay, it's a named distribution. So I want to first give a primer on what that distribution is, and then talk about the actual model, because the model is going to use this type of distribution. And so it's called a Dirichlet distribution. So how many other named distributions do you know? So beyond Gaussian, what other named distributions do you guys know? Poisson, gamma, beta, uniform, sure. Exponential, what is it? Yeah. So there are many named distributions, right? So Dirichlet is also a named distribution. It generalizes what is called the beta distribution. Okay, so what is the distribution over, right? So Dirichlet distribution is a distribution over vectors. Okay, these vectors are such that each coordinate of the vector is non-negative. Okay, let's say the distribution over 3-dimensional vectors, because these pictures are in 3 dimensions. So let's say that this Dirichlet distribution is a distribution over 3-dimensional vectors. What you want to ensure is that those vectors are such that each coordinate of the 3 dimensions, each of the 3 coordinates, each number is non-negative, and they also sum to 1. Okay, so that's the constraint on the vectors which are part of this Dirichlet distribution. So if you sample something, it's going to be a vector, but it's going to have these 2 properties. They are non-negative and they sum to 1. Okay, so that's why you're seeing something like a triangle, because if you think of a non-negative numbers, but they have to sum to 1, they happen to be lying on a plane. Okay? So if you think of 3 dimensions, x, y, and z, right? So 3 dimensions, but the numbers are such that they need to sum to 1. That's a hyperplane, right? So x plus y plus z is equal to 1 is a hyperplane. On top of that, you want to ensure that x is greater than 0, y is greater than 0, and z is greater than 0. That means you're chopping off that hyperplane, because some parts of the, x cannot be negative, y cannot be negative, z cannot be negative. And that chopped 2-dimensional plane in a 3-dimensional space is going to be like a triangle. Okay, and that's why you're seeing a bump on top of the triangle. It's just some sort of a distribution sitting on top of that. So think of this as a Dirichlet distribution. So if you pick a vector, most likely you more than often than not, you'll get vectors in this region, but you'll also get vectors in this region also, with lower probability. Okay, so that's all a Dirichlet distribution is. It's just a sampling from a space of vectors. Okay. Yeah. So if you think of the beta distribution, which is as I said, is a special case of Dirichlet distribution where you don't have a vector. I mean, you effectively have a vector in the sense that beta distribution produces, you can say canonically produces 2-dimensional vectors, because if it produces 2-dimensional vectors, there are 2 numbers. They have to sum to 1. So kind of the second number is redundant, because if I get a 1 number, then the second number is just 1 minus that, right? And the number has to be between 0 to 1, because if one of the numbers is not between 0 to 1, then the other number, cannot be between 0 to 1 as well. Okay, so you can't exceed 1, because there is a second number which has to be non-negative. So beta distribution, although if you think of, like, if you go to numpy or scipy, you can sample from a beta distribution, you get 1 number. But effectively think of that as one number and then 1 minus that number as a two-dimensional vector that's being generated from the beta distribution. Okay. So beta distribution, which is well known, is just a special case of the Dirichlet distribution. Any questions about this? I mean, this is something, if you've done 570, you've seen name distributions, obviously. But this is just one additional distribution. Okay. So with that, let's actually talk about the model. Okay, so what are we modeling? Let's talk about the problem statement and then the solution, right? The problem statement is I have a collection of documents. Okay, what are documents? There is a collection of sentences. Okay, I have a collection of documents and I just need to cluster them. Okay, I mean, I'm using the word cluster a little bit informally, but we basically need to basically slice and dice this bunch of documents, and we need to obviously slice and dice it not manually. I mean, we want to apply an algorithm on these documents such that we'll get some resultant additional like metadata or some derived numbers through which we can just separate out these documents into, oh, these documents are about sports, these documents are about politics and so on. Okay, that's what we want to do. So topic modeling is the general name. So it is a type of clustering in the sense that it is the type of unsupervised learning. Okay, there are no labels here. It's just a bunch of documents, so a bunch of data points effectively. And we just need to kind of put them into topics or basically cluster them. You can think of topics as clusters if you want, informally. And so that's what we want to do. So that's the problem statement. Okay. So there are many ways to achieve this, right? So you could look at just, if you did not want to do latent digital allocation, what is a naive way to do it, right? You would know, you just see look at the distribution of words in each document, and maybe some documents have similar distribution of words, maybe they are closer, and some other documents have maybe very different types of words, then they'll be far, they should not be close to each other. So you could do some, naive way of, you could do some way to kind of put the documents together so that some documents are close to each other. You just call it a topic 1, topic 2, and so on, and then you can post hoc give an interpretation. The same, something more, something like that is happening here, not just distribution of words, but these words like politics, religion, and sports, they're also assigned post hoc. So it's not that the model is just telling you, okay, there's a collection of sports related documents here. It's not. It's also creating some extra metadata through which you can say, okay, these are all documents that should be together. And then you look at the documents, and then okay, maybe it's sports. Okay, so that's what we're doing. So there's nothing magical happening here. The application is just like clustering, right? So any new document, you can say, okay, once you do clustering, you can actually use the cluster labels as some sort of targets, some sort of prediction targets, right? So here, if you're in a new document, you can say, okay, what is this document about? It's basically saying whether it belongs to cluster 1 or cluster 2 or cluster 3 or cluster 4. Okay, so it's basically some sort of classification you can do, right? So LDA is quite popular for many different types of data. So you could have, data from social media, which is not going to be huge documents. It's just going to be small, like comments and tweets and things like that. So you can work with that type of data, and it works well. It also works with long form articles as well. Okay. So what is the model, right? So this is an example of a generative model. We have seen a generative model before, which is a naive-based classifier. Okay, but typically generative models have a very mechanical way of explaining them, in the sense that how do you explain a generative model? One way to explain it is to actually talk about the generative process. Okay, so if you knew all the parameters of this model, how would you generate all the random variables associated with it? Okay, so for example, for the naive base, there's the x's and y's. If you had all the parameters of the naive base model, there's a way you can generate the label and then generate all the features given the label, right? Why? Because we have the conditional independence assumption. We have all the parameters. So you can first generate the label and then generate the xi's given the label, because they're all conditionally independent. Okay, so there's a generative story for naive base as well. It's kind of simple, so there's nothing deep there. Here, the generative story is one of the easy ways to understand what's going on. So let's forget about estimation for a second. We're not doing any estimation. We'll just talk about the generative story. Okay. So what is generative story? So generative story means what are we generating, right? So we are generating a document. So because documents are the kind of the only objects in this problem, right? So we're going to generate a document. Okay, so this is going to be very unrealistic because it's a probabilistic model, but this is what the model thinks of how to generate a document. Okay, it's going to be unrealistic. It's not going to be like modern LLMs or anything. So first we generate what is called the topic distribution. Okay, it's called topic vector. So for simplicity, as I said, we're not doing any estimation, so we already know beforehand some of the quantities here. I'll point them out. And for example, we also don't know the number of topics. Let's say there are 3 topics, just like in the previous slide. So we already know that. So what we'll do is sample. This is the generative process, right? So we'll sample a topic distribution theta. Okay, so that's going to be 3-dimensional, and it's going to be sampled from a Dirichlet distribution. Okay, so because if you're sampling, you have to sample from some distribution, and we're going to use this name distribution Dirichlet, which I introduced in the previous slide, and it has its parameters alpha. Okay, alpha 1 to t is just a shorthand to say alpha. There's alpha 1, alpha 2, alpha 3. Okay, because there are 3 topics that we have. Okay, so this is very similar to beta distribution. Beta distribution has 2 parameters. Okay, parameter 1, parameter 2. So they control how the beta distribution looks like. So similarly, Dirichlet distribution has, however long the vector you're trying to generate, that many parameters are going to be there. Okay, so we're going to create a topic distribution vector. We're going to sample it. It's going to be 3-dimensional. Okay, and what is a nice property about it is that the theta is actually a probability mass function itself, because the coordinates of theta are non-negative and they sum to 1, right? That's by definition of the Dirichlet distribution. Okay, so that theta is 3-dimensional. So for example, think of a theta being equal to 0.50, 0.49, 0.01. Okay, but that's not prefixed. That's just when we draw from the Dirichlet, we got this 3-dimensional vector. Okay, so that's the first step. I mean, here we're calling alphas to be hyperparameters, but just think of them as parameters. They're not random. They are one of the only things that are not random. But theta is a random thing, okay, which we sample. Okay, so I mean, there's some relation between theta, what is the mean of this theta vector and so on. So let's ignore that statement for now. Okay, it's nothing deep, but let's ignore that second statement here. So let's go to step 2. We generated a theta, which is a probability mass function. Step 2, we're also further going to assume that we're only going to generate n words in my document. Okay, some capital N that's also predetermined. Okay, let's say 1,000 words in my document. So that's fixed. Okay, so we're only going to generate a 1,000-word document. So for each of the, so we need to generate the words now. Okay, so the way we're going to do it is first generate the topic that the word comes from, which is step 2, which is to say the following. Since we have the theta, which is a probability mass function, let's say we sample from that. Okay, for the first location. For the first location, if we sample from something like this, maybe the first location says, hey, the first word should be related to the topic weather. Okay, maybe again we sample for the second location. Second location, maybe we'll get, okay, hey, the second word should be from the topic finance. Okay, and again you sample for the third location, maybe it's again weather, and maybe the fourth location it's sports, and so on. So what we are trying to do now in step 2 is say what is the topic what is the topic that the word belongs to. So it's like you have 1,000 blanks. Since we're trying to do a 1,000-word document, you have 1,000 blanks, and for each blank, before filling the actual word, you're just trying to fill in which topic is associated with that blank. Okay, that's the intermediate step, step 2. And then since we know for every blank we know which topic it's associated with, there's going to be another set of parameters, beta. Yeah.
So individual words are associated with only one topic, or how is that?
Yes. No, I mean, individual words will be associated with, it's not about, okay, let's rephrase what you said. So you're asking whether words are associated with one topic only or something, right?
Yeah.
That's not true. So that's what I'm trying to say. Currently we have put blanks, and we are associating the blank to be which topic that blank is related to. Why is that useful is in the next step. So this is, we already know theta, so from which we can associate, we can sample from the PMF. So we got all these Z's, which is which topic that blank belongs to. I kept saying word, but we don't know the word yet, right? So it's a blank that should be related to that topic. Okay. Now we'll have another set of parameters, beta underscore zj. So actually zj is a random variable, right? So it could take value weather, finance, and sports. Those are three values that zj can take, zi, and that every blank can be either weather, either sports, or whatever. What was the third one? Finance, right? Weather, sports, or finance. So this beta is now another probability mass function. It's a part of my estimation. Okay, this beta is going to be a probability mass function over all the words in the dictionary. Okay, so let's say there are 50,000 words in the dictionary. Beta is going to be a distribution, a probability mass function over your dictionary for each topic. Okay, so there are three topics: weather, sports, and finance. Under each topic, there's going to be a distribution over all words in a dictionary where, for example, if it's sports, then the sports words will have higher probability mass, and other words probably are low probability mass. Okay. Similarly, if you are under weather, then the weather-related words will have high probability mass, and everybody else will have low probability mass. Okay. So those three really long probability mass vectors are already available. Okay. So remember, we are not doing estimation here yet. We know these, and then we're trying to generate a document. Then all we're doing is condition on the blank being of certain topic type. We're just drawing from that probability mass function over the words to just get a word. Okay. And so after that, we're just getting a very incoherent collection of words where, which correspond to basically the topic proportion that we sampled from. Okay. So that was the generative process. We sampled the topic proportion, basically the theta, and then we said, okay, each word location, which topic would it belong to? Which roughly will correspond to about 50% of the blanks will be related to weather, on average, and 49% of the words blanks will be related to finance and whatnot. And then you're actually filling the blanks with some learned probability mass functions over these one per each topic. So there'll be three of these betas. Okay, one per topic, and then appropriately whatever zi value is, appropriately that PMF is used to get the actual word. Okay.
Okay.
Yeah.
These distributions that in step 3 you're talking about. So
yeah.
For each topic, right? Weather, finance, and sports.
Yeah.
So let's say you have like the weather distribution.
Yeah.
So why do the non-weather words even have like mass at all? Because you mentioned that they would just have very small mass, but not zero.
No, I mean, I didn't say that they could have zero. I mean, we're not constraining that at all. I mean, these are estimated through an estimation process. And so we are not explicitly constraining them to be non-zero or zero or anything like that. Yeah. Yeah. But they have to sum up to 1, right? It's a probability mass function. So if somewhere the mass is high, somewhere else the mass has to be low. Right? Yeah.
So I just want to understand what you're telling me. So we take a blank, we don't know what the word is inside it.
Yeah.
And from the probability mass functions of the dictionary that we already have for the topics.
Yeah.
For each of topics, we get a list of words for that particular blank.
No, we sample. So if we know that location, let's say ith location should be since we assign for the ith location which topic it should be, let's say it's for the weather topic. That's what we're doing in step 2. Every location we're assigning which topic it should be. Which topic
are you assigning that?
So zi is a random variable that's sampled from theta. Theta is 3-dimensional, right? So it's saying theta is exactly this, like 0.50, 0.49, 0.1. If you sample something from this 3-dimensional, 3 length probability mass function, you'll either get weather, or you get sports, or you'll get finance, right? One of these 3. So every location you're saying, okay, whether it's related to topic weather, related to topic finance, related to sports topic. Right? Zi is a random variable, which is like assigning a tag to each blank where you're not filling the word yet, but each blank you're saying which topic is it related to or belongs to, or, I'm just using informal words here, but basically for that blank, you're saying which topic would you need to sample from. That's basically technically what we're doing, right? So zi, so you would have weather, sports, what was that one? Finance. You'll have a sequence of such weather, finance, sports, blank, tags associated with each blank. Now you're saying what word could go in there. You just get it from the distribution of the dictionary. For each of the topics, there'll be potentially a different distribution, and you get a word from the dictionary. Yeah.
For example, we have lots of documents, right? For each document.
No, forget about the lot of documents, right? This is just a generation of a single document.
Oh, it's a single document.
Yeah.
And in single documents, we are assigning each blank.
No, we're generating a document. We don't even have a given, nobody gave us a document, right? If we know the parameters of this model, can we generate a document? That's what we're doing here. That's what a generative process is. Like a generative process is about, if you know something about the general distribution of random variables, you should be able to generate those random variables, right? So that's what we're doing here.
So we're just taking random blanks and then filling out them with
random words, basically. Random as in based on this probability mass functions.
But since they have different topics, how can they be a coherent topic?
They will not be coherent. This document is not going to be coherent at all. It will not be, obviously. Yeah.
How is it useful?
No, this is just a description of the generative process to tell you what is the ingredients involved here, right? So there is random variables. So there is a beta, which is a distribution over topics. Distribution over words given every topic. And there is a distribution over topics themselves, okay, which is alpha. Now, these two are the parameters that you need to learn from these documents. So basically from these documents, you need to learn basically a distribution over all these words, okay? If let's say the number of topics is 3, then you will learn a number for each word in the dictionary. So this list will be the same for the length of the list will be the same, except the top words in each topic will be different, okay? That's what you learn, estimation. Okay. You'll also learn what is the proportion of politics, what is the proportion of religion, what's the proportion of sports. Not just the proportion, but the alphas corresponding to the distribution. Okay. And then once you learn that, then any new document you can actually estimate, given that this document happened, what is the theta? Okay, what is the theta? You can actually figure that out. So think of it this way, right? I told you the generative process to get to a new document. And now if I give you the document, you should be able to get what is the theta that's most likely corresponding to the document, right? It's like conditional probability. So all these are random variables. Even the document that was generated is a random variable because every location is like a random word that I sampled from things. Now, if I observe these random variables, what about the random variables that I did not observe? Right? If I know the estimation, let's say from previous documents, I already estimated alpha and beta, and now I've been given a new document, I've observed it. Now, can you tell me what is the unobserved random variables values, which is unobserved random variables here? In particular, we are interested in theta. What is the unobserved random variable theta value for this? Okay. Okay, and so that unobserved theta will have some probability, condition on the observed document. There'll be a distribution over theta, and so that will tell you what the topic proportion is for that document. So it's exactly conditional probability for a joint distribution, right? If you know some random variables, you can ask what is the probability that the remaining random variables that I did not observe, what values did they take? For example, think of two Gaussians. They're correlated nicely, so they have a very a covariance matrix which is like heavy on the diagonal. Okay, so if you observe that one of the Gaussians is like value 10, then obviously the second Gaussian might be around the same range rather than like a minus 200 or something, right? So all I'm saying is the generative process is telling you how all these random variables realize. The random variables here are theta, zi's, and wi's. Okay. Now, if I tell you what the wi's are, which is the words themselves, you should be able to tell what the other random variables could be, right? What the zi's could be, what thetas could be, or what the theta could be, sorry, for that document. And that's what we are doing. Okay. So you should be a little bit more comfortable with joint distributions and conditional probabilities. Then this seems like a pretty natural thing. Actually, I think there are no detailed examples, but here's the yeah, I mean, I already explained what this is. So this sampling is exactly the third step of that process. So basically what are we doing, right? In the estimation step, we're going from a collection of documents with no labels to getting a distribution over words. That's all we're doing. The beta yeah, the probability of a word under each topic, topic 1, topic 2, topic 3, probability of every word in my dictionary. That's what we're computing. Okay, so those are the estimated parameters of this model. And there is another set of parameters, which is the alpha 1 to t, the parameters of the Dirichlet distribution. Those are the two sets of parameters that we need to learn given a corpus of documents. If we learn that, then every document, given any document, we can figure out what these latent variables are, which are, what are latent variables? In our data set, we don't observe these, we don't observe theta, right? Any document is just what words we observe. We did not observe theta and ZIs. So those are latent variables. And that's why the word latent there. And Dirichlet allocation is because the generative process starts with the Dirichlet distribution, sampling from a Dirichlet distribution. That's why it's called Dirichlet allocation. Okay. So you may say, okay, this seems like a pretty complicated model. Is it actually useful? Yeah, it actually, it was proposed 22 years ago or 23 years ago. It has been used widely, as I said, for all sorts of corpora, and it's a good hammer to use if you have an unsupervised learning problem like this, where you want to kind of, throw in a bunch of documents, get some topic distributions, and then interpret the topic distributions by looking at the top words under each topic. Maybe maybe they are kind of unique in some sense. So obviously you might have sometimes topics which are mixed, like it could be both politics and sports, which is not like that interesting, but you could get these very interpretable collections of topic themes. Okay. Any questions here? So now, yeah, I think this picture, I don't want to confuse you more. It's just exactly the same thing, the topic distributions, which is the distribution of words in the English dictionary under each topic. For example, here 4. And the Z's correspond to each word, what topic it belongs to. And the word itself is sampled from the appropriate, like if it's a pink one, then you sample the word from this probability mass function. And the topic proportion. So what I'm saying is, if you observe these words, then you can, given these parameters and given the alphas, which I don't think I've shown here, given these parameters and the alphas, if you observe the words, you can get what was the latent variable, which is the theta. You can get a probability distribution of that, and so you can get some sort of what's the likely theta value, which is theta is supposed to represent the topic proportion of each document. Okay. So for example, let's say the proportion was such that pink is really small, blue is really small, and yellow is really tall. Then you can say that that belongs to that yellow topic. Okay. So that's how you're inverting, like given the observed things, and figuring out what's the most likely topic for this document. Okay. Now I did not comment about the estimation. The estimation is actually, so what is the estimation? So you have a bunch of random variables. For naive-based, the estimation was easy. Why is it easy? It's because if you write down the maximum likelihood estimation type of, you can write down the likelihood of data given the model here. For naive-based, it's a simple maximization problem, and that maximization problem actually tells you, okay, count and normalize. Basically, look at the occurrence of the label and the word divided by the number of occurrences of the label and so on, right? So maximum likelihood estimation for naive-based gives you a very simple formula, but here for this model, this generative model, maximum likelihood estimation doesn't work. Okay, it's complicated. So there are some computational ideas to kind of actually estimate for example, these things. Okay, there's some additional computational ideas to estimate these things. If you have, it's very similar. What I'm trying to say is that the complexity of estimating these topic distributions, for example, is very similar. I wouldn't say similar, but like, have you heard of Gaussian mixture models? Gaussian mixture models for clustering. You can use Gaussian assumptions on your data points and assume that there are three clusters or 3 Gaussians, and then you'll learn the means and variances and whatnot. So that also you can, if you do maximum likelihood estimation, it doesn't work that well. And that's why there's this procedure called expectation maximization, EM method. If you are doing 575, you might come across this in machine learning. So there's ways to kind of circumvent the hardness of maximizing likelihood directly. Hardness as in like computational challenges of maximizing likelihood directly. And so similar idea needs to be not just EM, but some extra ideas need to be added here to do the estimation. Okay, but somebody has worked that out 20 years ago, so it's not like we have to. We can learn it, but for now, we just want to appreciate. Okay, this is a generative model, and it can be used for topic modeling, right? Basically clustering. So that was my brief remark about estimation. Now this picture is very similar to the figure that I had for naive Bayes. I just wanted to show that that naive Bayes figure was not just a one-off representation. In this field, the generative models in general these are also called probabilistic graphical models. In this field, there is a simpler notation that was, that's kind of common, which is called the plate notation. You just have to, instead of replicating like a lot of random variables, into a graph, okay, which is what we did for naive Bayes, right? There was a y random variable, and there was this w or whatever x, multiple random variables related to the occurrence of the word or not, right? So similarly here, things outside this box are basically parameters. The alphas and betas are parameters. So the same, the betas are topic distributions, alphas are the relationary parameters. And then the generative process is easily read from this picture. So from alpha, you sample a topic distribution for the document, a 3-dimensional vector, for example. Given the topic distribution for the document, you find the topic for every word. And since you know the topic for every word, now you sample the word itself. While sampling the word, you need this extra thing. That's a simple notation. I mean, it's just a common notation that's used in this area. Okay. Yeah, let me skip this slide. Any questions about LDA? Okay. So, I don't know if it felt unsatisfactory. It is a little bit unsatisfactory because it's working on text data, right? Corpus of words, corpus of whatever sentences. But there is no explicit modeling of the words themselves. I mean, there's obviously you are clustering documents, so somehow you end up with distributions of words such that you might be able to distinguish between topics distributions, but there is no really semantic aspects of words that are captured. There is some obviously frequency characteristics of words that are captured in this model, and that's why it is able to cluster documents. It lets us cluster documents. But really, the word level meaning, or there's no embedding of the word, and that's what we'll get to in the next rest of the lecture, which is that if there's a word the word cat and the word dog, and there's a word house, maybe cat and dog should have vector representations that are similar compared to the vector representation for house. And this model doesn't have any vector representation for anything. It's just conditional probabilities and distributions here, probability mass functions. Okay, so the next one gets us closer to our embeddings idea. So let's come back to sentence classification. The naive Bayes model was also doing sentence classification. In between, we went to Markov models and and LDA, but let's come back to sentence classification. Okay, I mean, spam classification was also sentence classification. It's the same thing. It's just a sentence and a label, a binary label, right? So there are several ways to kind of approximate, to kind of reduce the complexity or change the complexity of the problem. One is, so if you input a sequence of words, which could be variable length, right? In naive Bayes also it's variable length, except we know that the number of words in the dictionary is like fixed, so we are able to kind of handle it. So in this situation, there are many things you can do. One is like ignore the ordering of the words. So that's literally one hot encoding, so you don't have to worry about which word came first, which word came next. Obviously, you can also ignore semantic information. We'll talk about this in a second, but basically we don't really care about what words there are. It's basically, again, one hot encoding type of thing, which is what I'm saying, right? So fixed length of bag of words. And so this actually leads to, from a variable length input to a fixed sized one hot encoded or some frequency of each word type of a fixed representation, and then you can just do a binary classification using logic regression or something like that, right? But you could do something else if you had what I call word vectors. Okay, so this is something we have not seen, but okay, so this actually is the same as the first point here. I'm just, by the way, ideating how to go from how to do sentence classification here. So nothing deep here. So if you had word vectors, for example, even 100 word vectors, right? If you just add them up, that's exactly bag of words representation, right? But if there were, some weights associated with it, weights associated while adding up these words, for example, it might, you might be able to kind of capture some semantic information. Okay, so I'm not saying it does always retain semantic information. This is just thinking. This is just they're not really concrete models here. So given this type of intuition, okay, maybe words, we need vectors representation words. Obviously, 100 is the way to one of the ways that we kind of naturally think of. That leads us to a idea which I'm going to present next. Okay, we have seen CNNs before. Just to recap, not about the whole of CNNs because that was a full lecture or 2 lectures, but for NLP, they were, some folks started thinking about using it for sentence classification and variations like this. Okay, and they're less prominent today, so you would not think of using CNNs for working with text, but they do work. Just to kind of recap, one of the layers of CNN is a conv layer, and for the conv layer, if you have filters, the filters slide over this input tensor generally, and they produce a number, right? So it's basically a linear operation, but just mechanically, if you think about it, it's just a filter element-wise multiplication with the input, and then producing a number. Okay. Now the filter the filter size and how much you're striding influence the output size, right? So because the filter size is 3 × 3 and the input is 5 × 5, and there is no zero padding and the stride is 1, that's why you got a 3 × 3 matrix. Okay. Now imagine if the filter was not 3 × 3 but 3 × 5. Okay, which means that these 6 numbers are also yellow. Okay, in that case, I'm not striding anymore, but in that case, I cannot go right anymore. I can only go down, right, one step. Like I can't move left and right, so that is a canonical. I can do one set of computation at each 3 rows, and then I just have to move down. Okay, all I'm trying to say is that if your filter was 3 × 5, instead of a 3 × 3 matrix, you would have a 3 × 1 vector. That's all. Is that clear? Just to kind of stretch your imagination a little bit with what we have already done, right? Any questions here? I'm not really recapping CNNs, but I'm just telling you the operation. Okay. With this, actually, okay. So this was just why CNNs, because they have some properties in images. Maybe they're similar properties that we can exploit for text. But how do we do that, right? So ignore the first bullet point. The second bullet point is important for us. What we want to do is that we want to somehow represent the sentence, like we're doing sentence classification or spam classification, they're all the same thing. We want to somehow represent the sentence as a matrix. Okay. What is its dimension? What is the number of rows? And what is the number of columns, right? So what we're going to try to do is that we want to represent each row, 1 row per word. So if the sentence has 10 words, then 10 rows. If the sentence has 5 words, then 5 rows. Okay. What is the number of columns of this matrix? Okay. If we just did one-hot encoding, then we know what the number of columns should be. It's just number of words in the dictionary, right? For now, we can, we don't have to worry about the number of columns, in the sense that, okay, worst case, we can just think of one-hot encoding if you want. Okay, so the number of columns, let's say there are some choices, one-hot encoding leads to the number of columns, a fixed number of columns, and then it's just the number of rows. It's not fixed, it's just whatever the sentence length is. Okay, sentence length is 10, then with 10 rows, the sentence length is 5, and 5 rows. Okay, so if you can do this, then the previous filtering idea can naturally be used. Okay, and that's being shown in this figure. Let's not worry about the text at the top for now. I mean, we'll read that in a second. Let's focus on this, what's happening with these arrows. Okay, so on the left side, you can see, just for illustration's sake, we chose the number of columns to be 5. Okay, and our sentence is, I like this movie very much. Okay, and exclamation also, is considered a word. So let's say there's a vector for that as well. Okay. So let's say for simplicity, these vectors are known, although we will literally after this is all about how to get these vectors and these embeddings. Or you can just think of them as these vectors as like one-hot encoding vectors if you want to. Let's say we have this matrix, okay, that we could somehow form. Then how do we do a forward pass? Okay, we're always thinking in terms of a forward pass now. We're not thinking of estimation first. Okay, estimation can happen later. We know how to estimate CNN parameters, right? We can just do backprop and somehow estimate the parameters. You just did it in assignment 2, question 1. So the way we're going to work with this is we'll create filters. Okay, so these filters are such that their number of columns is the same as the input matrix columns, number of columns. So these filters, so here's a filter which is 4 cross 5 because the width of the input is 5. Here's a filter which is 3 cross 5 because the input width is 5. Here's a filter which is 2 cross 5 because the input width is 5. Okay. These filters, you would think, you would want to slide, but they can't slide, so they can only go up and down. Okay. So think of this 4 rows overlapping with these 4 rows producing one number. And then slide by 1, these 4 rows producing another number. Slide by 1, another number, slide by 1, another number. But those are these 4 numbers. Okay. So it's exactly the convolution operation. Okay, except that instead of getting 2D activation maps, first of all, there's no depth here. There's no there's no tensors anymore. There's just matrices. Instead of getting a 2D activation map, we're just getting a 1D vector because the filters don't slide on the left-right dimension. Okay, they can only go up and down. And so because this filter had a length of 4, we got 4 as the output because we could only slide like 4 times. This filter has length of 3, so we could get a little bit longer vector because you pick 3, you get one number, next 3, another number, next 3, next 3, next 3. So there are 5 such choices, so you got a 5-dimensional vector. And similarly, this is like only 2, so you got even longer vector. Okay, and there are 2 such filters. So in this architecture, by the way, this architecture is from a paper from 2015. And so this architecture, the one proposed in this paper, they picked 6 filters at this layer. So 6 filters produce 6 2D activation maps, or I guess they're not 2D anymore, they're just vectors, except the vectors are different length. And so they just, what the authors did is they just pooled. Okay, they all made equal length by saying, okay, if there's a vector of length 4, let me put at number 1 by just doing a max pool operation or some equivalent actually. Yeah, one max pooling operation. And so they got one number per filter output. Okay. And then they just concatenate and they get a vector out of it. And then you just classify it as, and then from there you can just produce a score, right? From this layer is just a linear layer. And you get the 2 scores for 2-class classification. Right? Any questions here? So this is a forward pass of a using a CNN for a sentence classification problem. The only new things were that somehow you need to represent the sentence as a matrix, and that's about it. And then here we just use one con layer, but it's kind of hard to see how to use more than one con layer because you have restricted length and so on. But you could probably add more fully connected layers if you want some depth. But this is a very simple, yeah.
So how do we do convert this sentence into a matrix?
Yes. So what is the vector representation for I? What is the vector representation for like?
Oh, okay.
Yeah, vectors, right? So there's one vector per word. What is this vector? We know one candidate so far, which is just one-hot encoding, right? It's just, but you could do one-hot encoding, and that's where. So we have not discussed that here. You could use one-hot encoding, but we want to do something more than that. That's the rest of the lecture, actually, which is about embedding. So let's take a break for 10 minutes and then I'll talk about this, which is we want to move away from these previous models because they're not really capturing semantic relationships, semantic information about the words. Okay, CNN is doing it, but then CNN needs already those vectors. If you don't want to use one-hot encoders, it already needs some semantically, good representation or vector representation of words already. Okay, so we'll see how to do that right after the break. So let's take a break for 10 minutes. I'll resume at 9:34. Oh, sorry, 7:34. 19:34. Okay, I know this is the last stretch, but it's also interesting. We don't have to rush through anything, and I don't want to exhaust you guys, but let's see how this goes. It's a natural idea. This section, the goal is to really appreciate that we can capture semantically meaningful vectors for words, okay, which we have not done so far. I mean, all the LDA and CNNs and all that, they are just kind of not really attacking the root of the problem of how to represent natural language in a good way. Okay? And that's what's enabled all this natural language revolution that we're seeing over the past 10 years. So the idea we'll see is actually 10 years old. It's actually by some researchers at Google called Word2Vec. But that idea has evolved over again and again and again several times, leading to leaps and bounds impact. Okay, one of the impacts being way back 5 years ago, the same embedding ideas were actually used. Are actually some evolutions of them were used in, for example, Google search and stuff like that. So it's not just theory on some obscure research stuff. It's actually very useful, right? Even 5 years ago. So see. So what we want to do is some good way to deal with words, where what we want is semantically similar words to be represented similarly. Okay, that's our desire. So what are semantically similar words? Cat and dog are semantically similar. For example, compared to a cat and an airplane, okay? They're not semantically similar. Okay, we want to do that, and this is the idea. I mean, this is the design, and this is the idea leading to some models called vector space models. Okay, and how to realize that idea is by this what is called distributional hypothesis. Is that we don't know what like we'll have to otherwise go to the dictionary and say, okay, this word is semantically similar to this word, and we're not doing manual annotation of anything of what is semantics here, what is semantic similarity. Sorry, what we're going to do is that, okay, we have a hypothesis that words that appear in similar contexts share semantic meaning. That's the hypothesis that we're going to use to kind of tackle this semantically similar words being represented similarly. Because we don't have this metadata, or like, I would say master reference information of what are semantically similar words in our dictionary. Because there's so many words. For every word, obviously there are there are compiled resources like dictionaries and thesaurus and so on, which help to answer this first question. But we want to use this second idea, more, I guess, data-driven idea, that words that appear in similar situations, similar sentences, actually, context just means similar sentences or similar phrases, should share, they share semantic meaning. And so we know that, so somehow we need to kind of exploit the property that, hey, these are two words that are appearing in similar sentences, let's put them in the same, close to each other in the vector space. That's what we want to do. Okay. So if you kind of buy that, okay, if words appear in similar contexts, they have similar, I guess, they share semantic meaning, then there are a couple of approaches to kind of deal with this. One is I'm calling count-based, which is just somehow using counts of occurrences of words in similar contexts, very similar to assignment 2's question 2, where you had common users liking to movies, and just doing some sort of PC or some sort of approximation of that matrix of counts. Okay, Xij was the matrix of counts or liked counts in the movies case. Here there will be similar counts of, oh, okay, these two words, how many similar situations did they appear in? And once you have that count matrix, you can do some sort of PC or dimensional reduction or something, so that you can actually get vectors per movie or vector per word. Okay, And actually, that I forgot to mention that even in assignment 2, question 2, if you had Xij, you could just do PCA or something equivalent to that, like to get a vector for each movie also, right? So you did not have to do the square laws and all that. I mean, although the question was asking you to do that, but the moment you had Xij matrix, you could do PCA, for example. You didn't have to do anything else to get some vector representations for your movies. Similarly, that's what I mean by count based. But let's focus on the second approach, which is actually the one of the precursors to that we want to learn today, which is prediction based. Okay, so prediction based means we want to capture this, that words appearing in similar contexts should get similar vectors. I mean, because we assume that they share semantic meaning. That's our hypothesis. And to get those vectors, we'll use some prediction approach. Okay, which means that we have to create some prediction problem here. Just like sentence classification, we'll have to do some prediction problem here. So just to kind of ground, what do we mean by vectors? These vectors, we're going to call them as embeddings. So in particular, you can either say every word has a vector, and that's called its embedding of that word. Or you can say there's a function which, given a word, produces a vector for it. And that function can be represented with capital letter W. It's just some notation for the context of our understanding. It's not like a universally you're going to use the same notation everywhere. But so that's what we talk about. That's what we want. Okay, so some vector representation for a word, and just to kind of ground this vector representation, we have to set its dimensions. Let's say it's a fixed dimension of 300 or something. Why 300 here as an illustrative example? Because that's what was chosen by the folks from Google Research back in the day for a case study later on. And what is the example, right? So the function takes a word and produces a vector. Okay, and you just want these vectors to be close to each other if the words appear in similar contexts. Now, okay, that's what we want to do. And so how do we do that, right? So how do we do that? I think in the first slide I already mentioned we could do some count based stuff, which we will ignore for now. We will try to do that using a auxiliary task. Okay, so we will initialize W. So really, what is W, right? So it's given a word, it's producing a vector. So W is literally some sort of a lookup, some sort of dictionary, right? So given a word key, it's producing a value which is a vector. So you can think of it as a collection of vectors, essentially, which is represented like a dictionary, if you want. And so we have vectors for words. So what we want to do is fill up some random numbers in those vector, coordinates of each of these vectors. They're not they definitely don't capture the semantic, similar context means similar vectors idea. But we're going to change. We can consider them as parameters, just like you did in assignment 2, question 2. We're going to consider them as parameters and then tune them while we do an appropriate task. Okay, we're going to tune them. Okay. So what task, right? So this is prediction-based approach. So we want to kind of set up a task such that when we kind of do that prediction problem, we'll get good vector representations. Okay, good entries in each of the words vector representation. Okay, so here's an example task, and we'll see a more concrete task in a few slides. So let's say, just as a illustration, let's say we want to create a model that classifies whether an input sequence of 5 words is valid or not. Okay, so an input sequence of any fixed number of words, it's called an n-gram. So you might have seen this word somewhere. If not, it's okay. But it's basically n-gram means n corresponds to the number of words in that sequence. Okay. So for example, you can collect all sorts of sentences from Wikipedia and say and chop those sentences into 5-word lengths, and say, okay, operates the largest medical school is a valid sentence, and if you mess with one of these words, then you'll get an invalid sentence. Okay. So you can break half of these, you can break half of these 5-length sequences by replacing with an arbitrary word and saying that's an invalid sentence. Okay, invalid, sequence. Okay, so this way you generated, what did you do? You got some corpus, you synthetically generated some labels by just chopping from the corpora or corpus of whatever collection of sentences, 5-length sequences. They are assumed to be valid, and then pick those some other 5-length sequences, for example, and just randomly replace a word. Then probably it's invalid. Most likely it's invalid. Okay, so that's how you created a two class situation. I mean, here's an example of that, randomly changing a word. And then once you do that, you have a binary classification situation. So how does the classifier set up, right? So you have the words which go through this dictionary lookup, essentially, which is a function, but you think of as a dictionary lookup, where given a word, you're picking up that tensor, just like in assignment 2, question 2, picking up that tensor, and similarly picking up each of the tensors for each of the words. They might be initially random numbers. Concatenate them, for example, if you want, like you get 5 times the length of each of those one-dimensional tensors, and then pass it through some classifier. And it could be a logistic regression classifier, it could be a neural network, whatever, like 3-layer neural network. And then classify it as valid or invalid. That signal we already have. Okay, that value we already have. And then backprop. Okay, when we backprop, we can always backprop all the way to the entries or the coordinates of the W matrix also. Okay, so I saying W matrix because if you have a collection of vectors, you can just organize them as a matrix also, right? So where each index location just corresponds to the index of the word in the dictionary, for example. Any questions? Okay, I mean, this should be a little bit more familiar because you did assignment 2, question 2. Okay, or that should reinforce some ideas from here, to this, to that, and that to this. So obviously, in order to do good classification, it turns out you do want to learn W and C well. I mean, it turns out you will need to learn W and C well, and we'll look at a case study in a few minutes where we will learn W well through this case study of a model called word2vec, or the word2vec process to get embeddings. The task itself is uninteresting. Whether to classify a sequence of words as valid or invalid is just something we constructed, but it was really just a pedestrian thing, an intermediate thing. We really care about the quality of the W, the vector representations of words. That's what we care about. Our end result is not the classification accuracy, but the quality of the vector representations and whether they actually support some semantic information, okay, which was not there before. Or which was not there before in the sense of which we did not see in the models that we saw before. So at this point, we just described the task and we said, okay, if we do well on the task, we'll get good embeddings. So now we're just not getting into details of the task and actually how the embeddings are estimated. If some embeddings are estimated, let's talk about its properties and some additional ideas that we can think of. And then through the case study, we'll look at how it's actually estimated in the word2vec situation, which is a very popular embedding, I guess, approach that was proposed 10 years ago. Okay, so we'll kind of table the actual estimation of the, like a very good set of embeddings for later. But next talk about if we had embeddings, how do we think about it? This part is going to be similar to, for the CNN's case, if we had a CNN trained model, how do we know that it's good or not? We look at activation weights and all that. Very similar, not 100% the same, but somewhat similar idea. Say we had a learned, say we had a good W. Okay, one of the things that we saw with the CNN case was exactly what we're going to do now. So the second bullet point is just the sub bullet point is just talking about specific embeddings that were popular, that are still popular, called Glow and word2vec. Okay, they're just names for these embeddings. We'll look at one case study, which is word2vec, in a few slides. So what do you do if if you already have this embeddings or this vector representation for words already? Then you can just do projection, exactly what we did with image embeddings. Like when we had a trained CNN model, we passed all our training data and got this image embeddings and then projected down to 2 dimensions to see if the images of similar class like cluster together, right? So we'll do the same. This is a projection from some work a long time ago of some embedding. We can't really make out. So let's zoom into a couple of areas. This is a zoomed in kind of projection of these high dimensional vectors into 2 dimensions for words. Okay, and where you project it down to that point, and then at that point you replace with the word that corresponds to that vector. Okay, so here you can see that things related to quantities or numbers are on one subcluster here, and things related to days and days of the week and months and stuff are on one side of the subcluster. So there's just a visual inspection check to see, oh, if you learn some embeddings, if they have similar vector representations of words which occur in similar contexts have similar vector representations. Hopefully, when you project it down, there is potentially chance of like some distortion happening, but hopefully they kind of fall into similar two-dimensional space or three-dimensional space if you want. Okay, so that's what we're seeing here. So this is one way to kind of verify the quality of your embeddings. Okay. There are other things that folks have done in the past, and this is I guess this is something that we could also have done with image embeddings also, which is just that look at the nearest neighbors of some representative words. Okay, this is just saying like, okay, here's a representative image. Look at the nearest neighbor of Look at nearest neighbor images to this image, and if they are also of similar class or similar, whatever like the concept there is, then it's a good CNN. Okay, good embedding of the image in the image space, and similarly good embedding of the word in the vector space, right? So here, for example, the nearest neighbors of France in this particular paper from 2011, then 12 years ago, 13 years ago, this is what they said. This is the words they got as the nearest neighbor to that representative word. So they're saying that, okay, this kind of says that the embedding is kind of reasonable, pretty decent. Okay, but yeah. Actually, I'm gonna skip this 2 slides because I'm going to look at we're going to look at a case study, so it'll be very concrete of why, intuition of why the embeddings work. Let's talk about how much data, right? So obviously we have to see all the words for which we need to generate embeddings, in the sense that if we have the English dictionary and if you want to embed every word in the dictionary, that every word has to appear somewhere in the corpus. I mean, otherwise it's going to be, if the word did not appear in the corpus, how can you get a vector for it, right? But remember, we are trying to embed each word, and we want to have semantic kind of information captured in the vector representations. We don't have to see combinations of every word, in the sense that we don't have to see like if in 2 contexts, if 2 words appear in similar contexts, doesn't mean that we have to see every combination of contexts for which in which these words appear. Actually, I think I'm not explaining it properly. What I mean is that we don't have to look at every combination of, if word, let's say red, appears in some sentences, it's not like that red has to appear in with exactly the same, the word, let's say blue, appear with exactly the same words in other situations. Okay. What I'm trying to say is that if you think of red and blue as semantically like close, it's not that the context that they appear in, they have to be exactly the same. The combinations we don't need to worry about. It's not like if you see 5 sentences with the word red, then you have to see exactly those types of 5 sentences with the word blue. You don't have to. Okay? That's what I mean by combinations. Because we can generalize. Okay, because of this prediction approach, you can actually generalize as long as the contexts are reasonably similar. Okay, they don't have to be the same. Okay, so you don't have to see every combination with one word change to kind of do this. Okay, and that is similar to humans, right? We don't have to see every use of a word in a situation to kind of associate whether one word is related to the other word or not. Okay, so we don't need too much data. We do need data for all the words, but we don't need like a lot of data. Here are some more properties. I mean, what I'm trying to do is now try to think of, okay, if you had embeddings, we already said we can do some projections to kind of see what the quality is. There are some side effects that people computed, people observed, which is you can actually do vector arithmetic with words, and they have some that also kind of indicate that maybe the embeddings are good. Okay. So again, some sort of diagnostics, back to diagnostics. So for example, this is just an illustration of showing that if you have the vector for word, vector for, let's say, king, and a vector for queen, then the difference between vectors is another vector. It has some direction. That direction is kind of similar to the direction between, like, the difference between these two words. Okay, these are ways to kind of get a sense of whether your embeddings are, have some properties, and not just they have properties. Are they good? Are they capturing some directionality, for example, in this case? Okay. And same thing. So the difference of vector properties can also be captured through things like relationships, right? So, for example, France minus Paris has a vector. The difference vector is similar in terms of magnitude as well as direction to Italy minus Rome, Japan minus Tokyo, and so on. Okay, these are properties that you can observe if you had a good set of embeddings. Okay, another way to say this is that if you had good embeddings, these types of properties will come out. Okay. Again, this is from 10 years ago, so this 13 means like year 2013. Okay, so what have we done so far? I just illustrated that there could be a prediction task, this out of sequence prediction task, valid invalid sequence that might lead to good vector representations. We stopped there. We did not talk about actual detailed discussion of why there could be good vector representations. And then we said if there were good vector representations, then these are the types of things we could do. You can project down. You'll have clusters. You could subtract and see. You would have directionality being similar between similar pairs of words and so on. Right? That's what we have discussed so far. Next couple of slides, I'm going to just discuss some extensions to this embedding idea, the word embedding idea, because natural language is just not one language, right? It's not just English, and there's also other languages. So we'll have a couple of comments about that, and then we'll talk about the case study that I've been mentioning, which is word2vec. There will be very clear of why it turns out with the prediction task that the vectors do capture the semantic similarity. Okay, so that's where we're going. Yeah, we have already seen image embeddings and we are seeing word embeddings. We haven't seen a very concrete case study. Let's wait for that. So the next couple of slides is just a commentary about some extensions. So first extension, not extension, but like what do you do with these embeddings? Okay, and what else can you do with these types of embedding idea? Okay. Once you have embedding, just like with the image case, just like you use the image, just like in the image case where you use the pre-trained model as a fixed feature extractor, here you can just use these embeddings as something which are pre-trained, and you can just use them to get vector representation. So for the CNN sentence classification example, the matrix where we just chose the dimension D to be like 5 or something. How did we get that? We can just use a pre-trained embedding like this to get the vector representation for every word. Okay, so that's how they would be used for any downstream NLP task. NLP stands for natural language processing, right? So at least we know. So if we had embeddings, we can just use them as is, just like we can do for just like we can do transfer learning with fixed feature extraction for CNNs. Okay, so here are some other. So this is just the same idea what we said. Like, so if you have words to some word space, and we had some auxiliary task where we did valid versus invalid, and we somehow learned W really well, then we can just use it for some other task, which is, for example, our CNN sentence classification task, okay, which is actually a downstream task. Okay, so that's something that's just transfer learning. The next couple of remarks are about how to work with other languages and things like that. So the first remark is you can actually train this training process using a prediction approach to get embeddings for words. You can actually extend it to get embeddings for words of another language also simultaneously. Okay, so what do I mean by that? You can try to map multiple kinds of data into a single vector space. For example, a concrete example is you could try to do bilingual word embedding. Okay, where you have English words and Mandarin words, and you can put them in the same vector space where you could say, okay, for some words, you may know that these words are related to each other, and across the two languages. For example, the word university and this word here, they both should probably be corresponding, should both have similar vectors because they correspond to the same concept in two different languages. Then you can impose that as a constraint while training the vector representations, while trying to get the vector representations for this language as well as this language. So I'm just trying to kind of poke around the idea that if you knew how to create the auxiliary task and train one vector representation, if you have another language, you can actually use those constraints to also train the other languages vector representation. Okay. Any questions about? There's a picture in. Yeah, one of the outcomes of doing that bilingual word embedding is that words that we did not know were translations or like related concepts. You could get that if you did not know that before.
Certain submachines will be different, so we have to do somewhere in there.
We don't need sentence information is just a part for the auxiliary task, right? Yeah, sentences, let's say in this case, sentences written in Mandarin are not going to be sentences. Yeah, they will not be in the same order, for example, but that information is not being used. So what I mean, right? So if you think of vector space, this is just two-dimensional like projection of that. But all we're trying to do is there will be some words for which we know that they're translations. And for some words, we don't know their translations. When we are trying to learn these embeddings through an auxiliary prediction task, you can just impose the constraint. You can tie these two problems together by saying, okay, while we are getting these embeddings, just ensure that the embedding for university and the embedding for the a Mandarin word for university, they are actually the same. For example, you can just impose a constraint. Okay, how to impose a constraint? Just say v1 minus v2 2 norm square should be small. Okay, yeah. So you can learn embeddings together for multiple languages. What's the advantage of doing this is that if you don't know for every word what's the corresponding word in the other language, because of this auxiliary prediction task and this constraint on known words, the unknown words may align. Okay, may align, may not align, but most likely they might align. Okay.
So what you're saying is that since we had already a list of sentences in English, right, and we embedded those words through those sentences, there's some behind them. So how do we import the Mandarin words together with do we give them some Mandarin sentences as well? Or how do
yeah. So here I'm just focusing on the alignment between two languages. Alignment between two languages. So you could, like, the base case is you can always train an auxiliary task and learn the embeddings for English, train an auxiliary task where you learn the embeddings for Chinese, right, or Mandarin. And all I'm trying to say is that if you want to embed, you could embed both of them in the same space so that you get, if you know for some collection of words, they belong to the same, they should they should have the same same vectors. There could be other words because of these constraints that you did not know beforehand that they should be kind of semantically similar, will be similar. That's all. So I'm not changing anything. It's still the same prediction approach to kind of learn the embeddings of these two, except you can constrain these two vectors to be, let's say if I choose both of them to be vectors of length 300 dimensional, but if I separately train them, there is no relation between, even if I know two words are actually the same in these two languages, they will not have similar vectors, right? I'm just trying to say if the known words, you align them so that they should have the same vector when they get into these 300 dimensional vector spaces, then the unknown words can also be aligned. That's what I'm trying to say. These are just remarks on if you know the prediction approach to getting embeddings works, which is what we talked about, some debugging and some properties. Then there are extensions to these ideas that people have pursued, which is like embedding two languages. And actually, the next example is even like generalizing to not just languages but images. Okay. While I will not get into the detail, it's exactly the same idea, which is that, for example, images have their own, like if you have pre-trained CNN, we can embed images into higher dimensional space, and you project down images of similar types will get to the same space, right? Same thing with words. So what you could do is embed such that for images for which, like for example, if you know that some images there is a label, then you know that the label and the images should be in the same area. Again, joint embedding, same idea. So putting them into the same vector space. Then you will see that the words for which there is no corresponding images, or images for which there is no corresponding word, they will be appropriately positioned such that you can actually get a label for those. You can get a label for those appropriate. Like if it's images, then you can get a word label. If there's a word, you can get close by images and so on. Okay. So it's just joint embedding. All I'm trying to say is that if you can get embeddings for English language, you can also get joint embeddings by, through English and let's say some other foreign language, or you can also get joint embeddings between images and images and words. Okay. So if this sounds complex, let's actually look at our embedding example. So this is just trying to show how to embed words and images together in the same space. Okay. There may be questions. I'm happy to welcome them if there are questions, but let's look at the word to vec example that will concretize the prediction-based approach. Okay. It's just a very concrete case study in the sense that it's a paper and it's word to vec embeddings are anybody can download and use them actually for any downstream task, like we saw, right? So if you have embeddings, you can use them for any classification problem as is, right? So we'll look at word to vec as a case study. So it's a predictive method rather than a count-based method. What is the outcome? Is the W that we've been talking about properties, oh, it's good and all that stuff. We want to get that W, okay, which is just a collection of vectors, one per word. And so you can just think of it as a matrix also. So, so here I'm saying vector representation of words that capture the co-occurrence statistics. Co-occurrence statistics is, is exactly what we said, like the distribution hypothesis saying if they appear in similar contexts, they should have similar representations. Okay. So there are two variations to this paper, the work that was done. The variations are like, there's no conceptually hard thing over here, but we'll look at one of the variations. We'll look at what is called the skip-gram model. Okay, and what is called skip and gram will become clear in the next slide when I have an example. Okay, but the variations are like very minor difference. I'll point out the difference if there's time at the end. Okay, so what are we trying to do in this section? We're just trying to concretize the prediction problem. Okay, the auxiliary prediction problem, so that we can appreciate that we do get good embeddings. Okay, for the words. So the skip-gram version is one version of this prediction problem that we're going to do. There's going to be a very simple neural network that will let us learn this vector representation for words, this W. Okay. In particular, the network is so simple, it's just going to be a single hidden layer neural network. Just one hidden layer neural. It's just it's like logistic regression model essentially, with a little bit different, right? And it turns out that the way we'll define this network is such that one of the weights just turns out to be exactly the weights that we care about for the vector embeddings. Okay. What do I mean by that? I'll show actually. Yeah, I don't have a picture here. So it turns out that network definition, remember, if it's just a one hidden layer neural network, there's two pairs of weights, W1B1, W2B2. If you recall from like lecture 2, right? There's two pairs of weights. Turns out that one of the weights, in particular W1, will just somehow relate the W1 entries, the entries of that matrix, to the vector representations that we care about. So it just turns out one of the, either the rows or the columns, one of those things will just represent the word vectors that we care about. Okay. So it's a very, very simple, there's no deep part here at all, no neural network craziness at all. It's a very simple single one hidden layer neural network. Okay. But before that, let's just talk about the task, the prediction task. I know in the illustrative situation, I said, okay, let's have a valid sequence of 5 words and invalid sequence of 5 words. It's very similar to that, actually. So the task is going to be, you'll pick a word in the middle of some sentence, and then if what you're going to do is your training data will be such that you pick a word, then you're trying to predict all the neighborhood words of that word. Okay, I mean, all will be too many. So let's pick 2 words to the left and 2 words to the right, and we're trying to predict those 4 words given this this focal word. Okay, so that's the task. So we're gonna make the network learn the probability of these nearby words given this focal word. Okay, so how do we do that? So input is going to be a word pair. Why is it one word pair? Because if I have 4 neighborhood words, then I can say, okay, my focal word should predict the first word, that's one pair. The focal word should predict the second word, that's second pair. The focal word should predict the third word, that's the third pair. Focal word should predict the fourth word, that's 4 pairs. So you can think of it as 4 pairs if you want. Okay. And the output, input is this word pair in the sense that this focal word should predict this word, and the output is going to be some distribution over words of which word is actually the nearby word, because we want to say that the word which is actually in that example nearby word is the word with the highest probability. Okay, that's what we want. Okay. So this nearby is just a window size of 2 to the left, 2 to the right. So that's just a minor detail. So here's an example to kind of show what the auxiliary task is, right? The auxiliary task is, let's look at, let's say, the third sentence here. This word is a focal word, brown, and given this word, we're creating 4 training pairs, which is going to be brown should be predicting the word the, brown should be predicting the word quick, brown should be predicting the word fox, and brown should be predicting the word jumps. Okay, those are 4 training examples, input-output pairs, that we generate from this region of the sentence. And similarly, for other regions of the sentence, you can get many training pairs. So there are a lot of training pairs that come about. Okay. So given this, so at least the targets, are just classes. Okay. So if you think of the English dictionary as it has 50,000 words, then it's just a 50,000 word classification problem. Okay. So output, is just going to be, you're going to produce a distribution of words such that if this is the example, hopefully your distribution of words is such that the quick word has the highest probability, right? That means I'm correct. So that means the network is able to predict the nearby word, right? So that's what we want to do. Okay. Any questions here with respect to what the data is? Because I want to go back to the network, which is a one hidden layer neural network. For simplicity, I said 50,000, so let's change it to 10,000. So 10,000 words in a vocabulary. Okay, I mean it's 10,000 words in the vocabulary. The input is a word. So what we're going to do is we're going to one-hot encode the word. Okay, so since our vocabulary is of 10,000 size, we'll have a 10,000 dimensional vector where everything will be zeros. Some coordinate will be 1, which corresponds to that word, index of the word. Okay. The true label, the target word is also, let's think of it as one-hot encoded. Okay, so that's also 10,000 dimensional vector. What is the network output? The network output is going to be 10,000 scores, which will be transformed to probabilities, and then you can just do a cross entropy loss comparison. Right? The true label, some coordinate has to be high probability, and you're just checking whether that coordinate is actually high probability or not. Right? So it's just what the input is. Input and output, given the previous slide, are just one-hot encoded vectors. Okay. So what does the network look like? Then this is one-hot encoded vector input. From here to here, there is a W1, B1 going on. So one transformation, right? It's a linear transformation, a linear layer. From here to here, there's the output layer, right? So it's the next set of W2, B2, right? Further, we're going to in fact drop any nonlinearity. We're going to drop the ReLU nonlinearity or any sigmoid nonlinearity from this picture. Okay, so it's really this pretty much the network where the number of neurons that they chose in their work is 300. Okay, in one version of the model they just chose it to be 300. Okay, so there's some transformation happening, and you get 300 numbers. And then some transformation happens and you get 10,000 numbers. And you want to ensure that the 10,000 numbers for a given word pair are such that one of the numbers is the highest corresponding to the right target word. Okay. Any questions about the network? The data input output is clear. The network is now defined. The loss function is just going to be cross entropy loss. So yeah, I mean, I just mentioned cross entropy loss is just the probability of the nearby word given the focal word, right? So given the word, brown, what's the probability, fox or something, right? So that's exactly what the loss function is. It's just a cross entropy loss. Okay, what is this hidden layer, right? So this is where, so in that network, we said there are 2 pairs of weights, and I already hinted that the first pair of weights actually just corresponds to the word vectors that we care about. Okay. So why is that, right? So let's say the hidden layer. So to obtain the hidden layer, there's a first set of weight matrices and weight matrix and bias potentially, right? So let's say that weight matrix is W0. Okay, so given the 100 encoded vector, you multiply it with this matrix, you get the hidden vector, 300-dimensional hidden vector, right? What we'll do for simplicity is just take the transpose of the hidden vector. So instead of thinking of hidden vector as a column vector, we'll just transpose it to be row vector just for our conceptual simplicity, which means that you'll just transpose instead of W0 times X, it will be X transpose times W. Okay, so where W0 transpose is W. It's just a transpose of that matrix. Okay, so what did I do? Instead of the matrix having 300 rows, I just made the matrix have 300 columns. Okay. Yeah. Right, and the number of rows of W is now 10,000. Okay. So what's happening here, right? So think of X is going to be one hot encoded vector. If I'm going to multiply a one hot encoded vector with a tall matrix, 10,000 rows and 300 columns, let's say it's a one hot encoded vector for the word cat. Okay, then all this vector operation is doing is pick up the row corresponding to the index which involves cat. Okay, so in the sense, let's say the cat is the 1,000th word among the 10,000 words. If I multiply this one hot encoded word vector for the word cat, all it's going to do from this matrix is just pick up the 1,000th row, and that's going to be the 300-dimensional hidden vector. That's all that's happening. So all I'm saying is one hot encoded vectors times matrices are just picking up rows or columns. In our case, it's just going to pick up the appropriate row. Okay, out of the 10,000 rows. So basically, the reason why I did a transpose here is that if there are 10,000 rows, each row basically corresponds to one word. Okay, and so it turns out that if the network does prediction well, we are kind of getting to the point where we're going to say that each row, since it corresponds to the vector for each word, that those vectors will be will capture semantic similarity, in the sense that if the words appear in similar context, the vector representations, the appropriate rows will have vectors which are going to be close to each other. Okay, or yeah, close to each other. Any questions here? Or is it like too? I mean, it's not a complex network, right? This is one hidden layer neural network where we are just interpreting the first set of weights to be the embeddings themselves. Right. Okay, so here I just said this was the original. I guess this was the W matrix. I'm just interpreting each row to be to be the word vector lookup table, where since the word vector is represented as one hot encoded vector, if you multiply it, you'll just get one of these rows, and you just call them the vector embeddings. Okay, so yeah, I just mentioned this. So cat has got some coordinate. Then if you multiply that one hot dimensional vector, you're just picking the row. That's sorry, I should have mentioned it with the slide, but here's an illustration. If you have picking up the fourth row is saying this as good as saying if you had a one hot encoded vector like this, then just pick up the fourth row. If the one was over here, you'll pick up the first row, and so on. Okay, that's what's happening with the first half of the multiplication. Okay. Now, let's say there's a word ants, and let's say there's a word cat. Okay, that's in a vocabulary. So what is happening, right? So in the first operation, we're just saying that okay, if our input word is ants, we're just going to pick up a vector corresponding to kind of ants. That's our basically the hidden vector computation. And then there is a subsequent computation with yeah, so we are only picking the neuron. We're only looking at the coordinate corresponding to car. Okay, so to get that number, there's an appropriate column that's picked, right? So there's a row coming in, appropriate column that's getting multiplied together, and there's one number that's produced. Let's say that column is for the word corresponding to car. Okay. And then you whatever that number is, it gets exponentiated, and this normalization is we have seen it before. It's just getting the scores to some probabilities. Okay, so So this is like really in detail, like what's happening for any arbitrary pair of words. Okay, car is unrelated to and, so hopefully you expect that this number is like kind of close to 0. But if if there are bees, maybe the number we want to have. Okay, so okay, so here's the key slide. I know it's written in text, but here's the key slide, which is that if two different words have similar context, okay, so two words have similar context, okay, which means that words are similar, that are likely to appear around them are similar, then the output probability vector for these two words should be similar. Okay, why is that? So remember our training example for two different words, let's say ants and bees. Okay, for ants, there's these words around it, nearby words, which are similar to bees and the bees nearby words. Okay, which means that when ants comes in, there's a distribution of words that we're generating, right? So when the input is ants, there's a distribution of words that we're generating. That distribution of words should be same as very close to the distribution of words that we generate, when we give the input as bees as well, right? So that's what we are trying to. That's what will happen. Okay. The output probability vector should be similar. So if two words have similar context, they're both predicting the same type of words. In the extreme case, let's say they're predicting exactly the same words, then given those two inputs, I should get exactly the same distribution, right? Output probability mass distribution. Okay. But now you think about the network, if the output distribution has to be the same, okay, then, and it's a linear transformation going on here, if the output distribution should be the same, and a linear transformation is going on, turns out that the embeddings should be the same as well. Okay, so think of two vectors, I'm transforming it linearly, which means that they are either, linear transformation just means the same rotation, same scaling, same positional shift. If you think of it really in terms of vector spaces, if the same transformation is going on to get to these core vectors, right? So if two score vectors are the same for two different words, then because it's a linear transformation, the two word representation should be the same, is what I'm trying to say. That's what's happening with word to vector. Okay. So if two words have similar context, then the words, similar words are likely to appear around them. That's, the nearby words are going to be the same, let's say, similar or same. If that's the case, then the output probability vector, the output score vector or output probability distribution should be the same for these two different words. But if the output probability distribution is the same, then because there is a simple linear transformation happening in the second step of this one hidden layer neural network, the inputs should be the same vectors. Okay, input should be similar vectors. The vectors for the different words should be the same. Why? Because the ultimate inputs that we gave here, which is the one-hot encoding vectors, they are exactly one Hamming distance away. There is no similarity information there. So it has to be the word vectors, which is the first matrix rows, which should be similar. Okay, because those vectors are getting linearly transformed to produce these output scores and therefore the output distributions. And we expect the output distributions the same because the nearby words are the same or similar. Okay, so I'm just trying to reverse engineer this very simple network to say why the vectors should be similar. Any questions, or is still confusing? I know couple of people are seeing the light of why this makes sense. Any confusion or no? Yeah, I mean, let me go back here since we only have a few minutes. I want to say, let's think of this here. Forget about these three, there are 4 rows here. Just focus on the third one. Think of the word, the quick brown fox jump. So let's say we have these 4 examples, right? So let's say these are the only 4 examples corresponding to the word brown. And let's say there are the exact same examples corresponding to the word black, just for illustration purpose. So brown is predicting these 4 words, black is predicting these 4 words. Then if you train a network to give an input brown, you need to have a prediction of the quick fox and jumps. If your input is black, you should again produce the same the quick fox and jumps. Okay, these are the same nearby words, which means that given these 2 different inputs, you need to have the exact same probability distribution. What is the exact same probability distribution? Maybe 0.25 on B, 0.25 on quick, 0.25 on fox, and 0.25 on jumps, and everywhere else 0. Let's say. Okay. If they have the same distributions, these two words, okay, and these, if you do one step back, there's linear transformation generating these probability distribution. If you do go one step back, the only thing left is the vector representation of these two words, okay, brown and black. Okay, those two have to be the same because the output probability distribution is the same. Because the input, the ultimate input, which is one hard encoding of brown and black, they are not similar. Okay, there's no, they're just one Hamming distance away. So the only way these two things, the final output can be similar, after the linear transformation, is that the word vectors should be similar. Okay. That's pretty much the concept here. Let me just yeah. So for example, I mean, now to generalize, like words like university masters will appear in similar contexts, so they will have similar word vectors because their nearby words will be kind of same, and you're trying to predict for two different words the same type of distribution, so they'll kind of get the same word vectors. Okay. So the network is relatively large. So even for the simple illustrative case, 10,000 times 300 is 3 million. 3 million numbers. Okay, which seems small, but 10,000 is not realistic. The number of words in English language is much higher. And also, in more recent situations, there is this notion of tokenization, which is not at the word level, but at the subword level, which means the number of unique tokens could be, I mean, some of these papers, some of the recent language models, they claim like billions of tokens. Okay. So there are too many potentially parameters if you do it this way. And so a lot of tricks are needed to kind of actually do this, even the shallow neural network, to get these word embeddings. And those details are in that landmark paper from 10 years ago on word2vec. I will skip the engineering tricks. Yeah. So you can actually download those weights from Google's website, and you can actually use any package. Here I'm just showing with a package called Jensen. You can look at exactly the same thing that we saw in terms of illustration. Like you can look at what are the nearest neighbors for the word good, what are the nearest neighbors for the word France, what are the nearest neighbors for whatever, and to do the analysis of whether this is actually a good embedding of these words that was achieved by these guys. Okay. So even if you do this type of a word2vec type of exercise, the quality of your embeddings you can assess by looking at nearest neighbors and same things that we saw and projecting down and looking at visually whether the appropriate words are clustered together and so on. So you can do that as well. Yeah, let's actually let's not worry about the continuous bag of word representation. It's a slightly different auxiliary task. It's the same auxiliary task, but looked at in a different way. So let me pause here. So what we've done today, just to summarize, we started with LDA. Then we talked about CNN-based classification, which is very simple. We just expanded the filters to kind of span the word length, and we represented a sentence as a matrix. And then we moved on to, okay, CNNs needed that sentence as a matrix, therefore they needed the vector representation. So how do we actually get vector representations? And one of the key ideas was that, hey, if you want to capture semantic information, maybe words that appear in similar contexts capture, semantically similar meaning. Okay. And so let's actually just try to ensure that words that appear in similar contexts have similar vector representations. And so there were a couple of ways to do it: count-based, which we did not talk about at all, and prediction-based, which is what, do some prediction tasks where somehow you end up with good, prediction tasks which capture this notion of, similar words appearing in similar context should have similar vector representations. Word2vec's architecture was like that, whereas prediction task was predicting nearby words. And so that leads us to this vector representation where they actually have the vector representation of words actually have semantic similarity with other words. Okay, so relatively they're positioned in terms of vector space in the right places. Like words related to days are in the right place, words related to countries are in the right place, and so on. Okay, so this is a big leap from one hot encoding and the other non-semantic driven ideas. Okay, so let's stop here. And we'll talk about some other models next time.